Hello everybody, welcome to the Delphicon 2023 session celebrating 28 years of Delphi, in which we will be talking about fair critical section, which is from the area of multithreading. The critical sections enable only a single thread at one time to pass through a block of code. All other threads need to wait. They are used every time memory is allocated in Delphi, and when applied to a single instruction on one variable like increment, decrement, compare, they are called atomic operations. The goals for critical section implementations are, of course, modest processing overhead, guaranteed not to lock up, low frequency of atomic operations, thread fairness, and mindful of thread context switch frequency. So what means thread fairness? All threads entering a critical section exit in the same order in which they arrived. This is the definition. The main cause of non-fairness are preemptive OS gives no warranties on the timing when individual threads will be resumed from sleep, the thread context switch. The non-deterministic nature of the operating system's sleep function, and these are two main reasons, and the result is that every time a thread enters sleep to wait, the sleeping time can be slightly different from thread to thread. When does thread fairness become a problem? So if we have a T parallel for loop, and inside of this loop we have one section of the code which is threaded code, and all the threads are running here in parallel, and then we have another section of the code which is single threaded and is inside of a critical section, so that all the threads need to pass one by one through this code block. When the time which is spent by threads inside of the threaded code block comes to be close to the time spent inside of the critical section block, and the number of threads waiting in the queue of the critical section because of this becomes to grow. This is when the thread fairness becomes a problem, because the queue, or the number of threads waiting inside of the cs.enter line, becomes much more than 0. Now the wait inside of the critical section. Some threads may enter the critical section multiple times, while others get stuck at enter and might be released only once. So performance penalty can be 2 to 3 times and be varying 2 to 3 times from run to run. This is one indication that we possibly have a problem with the fairness of a critical section if our threaded code has large variability from run to run. And of course, the greater the core count, the bigger the number of threads that we will launch, the bigger will also be the problem. Thread job distribution across 16 threads is on this example, and you can see that if the columns are cores and the blocks are the thread jobs, then the jobs will get accumulated on a few cores or a few threads, and several threads, in this case 3 threads, will remain unused. 3 cores will remain unused because one of or 2 or 3 of the threads will be stuck inside of the critical section waiting line, while other threads will pass this block several times. Here we have an example of the implementation of the fair critical section, and the main key point here are 2 counters. Every time a thread enters, it reserves the index which is determined with the enter counter. This counter is then captured inside of this function and used inside of a loop to determine when does this counter match the value of another counter which is incremented with the leave. This makes a very clean and simple waiting loop in which we have no atomic operations. The precondition is of course that the overflow checks need to be off, and try enter is also possible with this this line. The tricky part here are these two parameters where the exec counter, these two expressions, because the exec counter needs to be read only once from the memory, and then from this one value which is read, both of these expressions need to be evaluated before being passed to this atomic CMP exchange function. The compiler in fact does generate code which respects this requirement, and at least on Windows, Delphi will correctly generate the code for this try enter expression. As specified here, the overflow checks need to be off, and it was tested that the integers will overflow, and this does not represent a problem for the operation of this language construct. In this example we are using the sleep 0, but this can be customized for the specific requirements. For example, sleep 0, count the number of sleep 0 and then increase this to longer sleep times if necessary. And finally, if we look at what is happening with the atomic operations, every time we increase, we call the atomic increment, the parameter in the core is written from this core cache into the main memory, and because it is written in the memory, this memory address is invalidated in the caches of other CPU cores. And the same situation happens when we are calling the leave or exit. We are incrementing another counter, and again we are communicating the value or publishing the value back to other cores. If we do not call an atomic operation, the time needed for the change value to reach other cores can be longer. In extreme case, if the other cores are in a tight loop, the change value might actually never or indefinitely, or the situation could be such that indefinitely this value will not reach the cache of other cores, because all other cores maintain their own copy of the same variable in their own dedicated caches. This critical section is will cause a very high thread context switch rate, higher than what it will be triggered by the Windows operating system's critical section. These critical sections look like they could be used everywhere, but Microsoft, for example, recommends a frequency of less than 1 kHz per core. So we should not be calling any critical section which will result in a thread context switch more than 1000 times per second. This is a relatively strict requirement on the design of the code and of the libraries, of the runtime libraries, on the whole the whole software to reduce the number of sleep commands, of the wait commands and critical sections in general. This critical section solves one specific problem, which has to do with thread fairness. But if our critical sections are short enough relatively to other threaded code blocks, then this problem of fairness will never occur, because the waiting lines for the critical sections will most of the time be empty. We will now have a look at some benchmarks. If we want to consider the Microsoft requirements that the number of thread context switches per second may not exceed 1000 times per core on the CPU, this means in practical reality that we may not call get memory in Delphi more than 1000 times per second if we want to be sure that the thread context switches will not happen. We have here an example where we are testing and comparing different critical sections. One is this FIFO critical section, which is the fair critical section. Then this is the Windows OS critical section, and we have the simple critical section, which is many times used in Delphi, and you can have a look at the getmem.inc, what is being used inside the Delphi memory manager. What we are doing here, we have a very slim body of the critical section, a very short piece of code where we are just increasing two variables or three variables, and we are counting the number of times we can manage to capture the critical section with try enter, how many times we do it with enter, and the time it takes how many times we enter for every thread, and what is the maximum time, and then we display some statistics. So let's run this code and see what results we get back. Some results, and if we compare the fair critical section with the simple Delphi critical section, we can see that the timing of the code is approximately the same, that we have the same number of iterations, and that the sum is correct. These iterations and the sum is displayed so that we can see if the critical section is actually working as expected, because if there is an error in and multiple threads would enter the critical section, then the sum would be wrong. Below we display how many times does the thread sleep longer than 1 millisecond. We can see here that 0 times, and the maximum is rounded to the value of 1 millisecond. And most of the time here we see that the threads sleep very rarely longer than 1 millisecond, and the maximum is sometimes close to 1 millisecond. This is for the simple Delphi critical section. If we compare this to the T-monitor, we have here one loop which is using system.tmonitor. We see that the T-monitor finishes nearly 10 times faster than the simple critical sections when using such a short body to be executed. Now T-monitor, when executed on without multithreading, is of course slower than the and this simple critical section, but it shows its muscles when it comes to multi-threading. So the result is correct, and what we can see here is that we have many more sleeps that take much longer than 1 millisecond, and that these sleeps are in fact, or the weights, these are the weights inside of the critical sections enter. These weights are fairly long, up to 25 or 50 milliseconds sometimes, but despite these long weights, still the result is very good. So how does this happen? Because the number of times which the number of times that the critical section is acquired is reduced. It is reduced because when the T-monitor calls exit, it does not really exit, but exits with some delay and allows the same thread to recapture the critical section immediately again. And this will lower the thread context switch frequency. Because of the lower thread context switch frequency, those threads executing will be more efficient and the timing will be better. Now we have the Windows OS critical section. The timing is similar to the Delphi, but we see some movements here. So the enter command will sometimes be more than 1 millisecond, but still not much more. It does show some attempts by Microsoft by the operating system to increase the sleep times and allow other threads to be running without so many thread context switches. But the final effect, at least in this case, is not very much different not from the T-monitor, but from the simple critical section. Then if we go to the fair critical section and try to consider the spin weight is just a simple loop without sleeping, without calling the sleep function. We have a lot of sleeps which last much more than 1 millisecond, and we have the maximum which is close to 50 milliseconds. So there is a somewhat surprising result that there are so many cases where the enter is going to sleep so many times and the final timing will be so similar to what we already had before. Another interesting result is that the try enter is going to happen only in a few hundred or thousands of cases out of 10 millions, which is much less than 1%. Here we have a fair critical section which is using switch to thread rather than sleep, and you can see that the sleep times inside of the enter command are very short, and the maximum is rounded to 1 millisecond. These timings should be taken with great reserve, because if we run this outside of the debugger, now we are inside of the debugger, we will get different results, and when we run this for an actual application, it greatly depends everything on the thread context switch frequency. This is the paramount parameter when it comes to critical sections. We should basically use critical sections extremely sparingly within our programs, and if we consider the Microsoft requirement for 1000 thread context switches per second, this is indeed very modest, because here we are running 10 million in 5 seconds. For the reference, here we have one web page where Microsoft is talking about the thread context switching, and it says it is reasonable to have fewer than 1000 context switches per second per core, that each context switch takes the kernel about 5 microseconds on average, which is close to 10 microseconds sometimes. However, the resulting cache misses and additional execution time is difficult to quantify. And finally, we are looking at the fair critical section, which is using sleep 0. This sleep 0 can only be used for the computational threads which are not waiting for the input-output operations to be finished or to be involved in the input-output logic, because the kernel might not update all the related resources necessary to make decisions inside of the wait loop. In here again, see that the wait time inside of the enter command is nearly never bigger than 1 millisecond, and the maximum is close to 1 millisecond. The total timing is not neither good or bad. It is comparable with other implementations, and if we consider that we are sorting the threads as they arrive, and that we process and release them in the order in which they arrived, this extra processing is nearly free, does not cost us anything special. We are going to have a look at the try enter logic implementation, which is interesting to see how the compiler is handling the atomic compare exchange enter working. What code is generated by the compiler when we execute the atomic compare exchange, because these two expressions need to be evaluated by reading the exec counter value only once from memory. So it should be that this value is read once, then this expression is evaluated from the same register. And here we see that the value which is in AIX is reduced by 1. We read EDX once, we move it into AIX, into AIX we reduce the value by 1 to create the exec counter -1, and then we can be sure that the exec counter, which is at RCX plus this address, is read from memory only once before it is passed to the lock CMP exchange. If the exec counter would be read more than once from the memory, then on each read the result could be different, because other threads could already modify this value. And here we are again concluding our presentation. I hope you managed to learn something new, and see you at our company webpage and on the GitHub. So thank you very much for your attention, and wish you happy coding.
All right, great. Thank you so much for that session. These are one of those. Yeah, it's always interesting these deep technical sessions because there's like parts of it's like are just beyond me. I think that probably happens for a lot of people, but there's always interesting parts to pick up on there as well. So I think you're on here to join me for Q&A. I don't see any video, but hopefully you have
Yes,
good
can you hear
audio.
me?
I can
Can
hear
you?
you. Yes.
Yes,
Yes.
wonderful, Jim.
All
So
right.
the main conclusion would be that in some cases you can get 2 to 3 times more speed, and it happens if the threaded code is about the same length in times of execution as the critical section code.
Mhm.
So this is the main area where you would want to use something like this. And you
Yeah.
can see and you can see if you have this problem, if the timings are jumping up and down. So every time you run the code, you get not slightly, but 2 to 3 times different result.
Mhm.
And this means that possibly you have a thread fairness problem.
Makes sense. It's one of those things. A lot of times, that people ask me that like, what's the best way to do this, or is this better than this? It's like, well, it depends. And this is a great example of that. It's like, well, this normally would be good, but then, like you said, when you have in certain circumstances, then you see where you can have better performance by making by using this differently. So there's a question here from Patrick. Um, Says in Delphi, system sync objects, critical section, mutex, and semaphore are used the same way. Does it make a real difference? I guess which one you use.
It's like this, that mutex and semaphores are generally meant for more for interprocess communication, which is maybe one order of magnitude slower than what you have inside of the process, and the critical sections are used inside of the process. And as I explained before, you can have penalty up to 2 to 3 times if your critical section is not fair and the operating system does not provide a fair critical section.
Let's see if there's any other questions here. Looks like not. Is your code the show? Is there any of the code you showed off available for download, or can we collect it and make it available later?
Well, the code is part of our product. So let's say
Okay.
it is open source so that you can see it, but it's still under license.
All right. So
Because
which if someone goes
so
to
you
do research, if someone goes to your do research website, what should
yes,
they download to check this out?
uh, you don't have to download anything. You can write it the way you have it, the way you have
Okay.
it written in this demo, and it will simply work. You can of course also download our product because it's integrated into the product, and it's used also these concepts in the product itself. So you will benefit from the extra performance which comes from this area. But this is, let's say, one thing that stands out and is interesting perhaps to other people who are more tech savvy and would like to have an extra edge. And when they see a specific problem in their code, or they would say, okay, I need this building block, I would like to put
Mhm.
this into our system. It would make a difference for us, and then they would, let's say, buy our product for to get these features.
A couple of questions here. Carlos is saying, "Congrats on the technical details. Sorry if I missed this. Is it possible to have nested calls using fair critical section?"
It's like this, that the all the calls are always nested, so you have multiple threads which are calling the same critical section, but they are being queued at the entry point. So you cannot go into depth of something which is where you only allow one thread to pass. So you
Right.
only allow one thread, and that's it. You could have one more critical section inside of the critical section, but that it doesn't serve any purpose because you have already limited the number of threads to one.
Right. That makes sense. That makes sense. Patrick saying, "I suppose using system.tmonitor to lock objects in code for compatibility with threads is a good thing too."
Well, I have had very good results with tmonitor. Tmonitor is actually a feature of many languages. You have the same construct in C#. You have the same construct in C++. And also, I'm sure in other languages, especially like Java. And this is a special design. Maybe there was a paper done some years ago and everybody implemented this. And the T-monitor, as I explained, has this special capacity to reduce the the context switch frequency. So how many times does the kernel switch between threads? So even though it looks like we are switching the same number of times, it does some trick to keep the thread, even though the thread running, even though it looks like we have switched to another thread, but we didn't. And because of this, it gives you a performance which is closer to a single core, full single core frequency, full single core capacity, rather than something which is much slower than one core processing.
Another great example of how it's not, the answer is not always obvious. It's one of those things. Patrick says, thank you. Adding more cores doesn't necessarily, because you have to consider that. All right. I think that's it. If people want more information, they can check out your website, do-research.com.
Yeah,
right?
Yes, correct.
Oh, just no dash, just do research.
Correct.
Awesome. All right. Well, thank you so much, and appreciate your time, and appreciate all you do.
Thank you very much, Jim, for having me, and I hope to meet you many more times.
Yes, looking forward to it.
Yes. Good night, Jim.